Good afternoon, this is Schweitzer, and we're going to be doing a little answer key to thermodynamics mediation. With me, I have my thermodynamic tables. I have my bond energy chart, so I'm not going to be posting those on screen, so make sure you have them with you. So it's the solid ammonium chloride is dissolved in water, producing a cold effect in the cold pack. We're out the dissolving reaction. So Alright, let's grab a pencil here. And we're out dissolving reactions. Okay, so it's ammonium chloride. What bonds are broken? What bonds are formed in this process? Well, we're breaking ionic bonds. And we're forming and formed are going to be really just ion dipole. When the bonds are broken, is energy released or consumed? Well, to literally separate two items that are connected together, you need to add energy to break that bond. So energy is consumed. The sum of all the sum of all of the broken bond energies of the reactants is the sum of all the broken bond energies of the reactants greater or smaller or equal to the bonds of the product. Okay, now in this case, because it's cold, we're putting more energy in. Now, here's an important thing that people always kind of get understood. This is endothermic. Heat is entering the system. Is the system getting warmer? No. It's incorporating the energy into bonds and storing it. So the outside gets colder and everything gets colder. The whole thing is cold. And this for it would be greater than. All right. It took a lot of energy to break the bonds, but didn't get much back when you reformed them, hence it's cold. Complete the energy diagram of the process. Okay, so endothermic would look something like this. Stuff's entering the system. Ammonium chloride contains all three of these attractions: covalent, ionic, and long-dispersion forces. As a sample of ammonium chloride is heated, the blank requires the least amount of energy to break. Okay, so that's the London dispersion forces requires the least amount of energy to break, and the ionic requires the most energy to break. All of the processes in question D are describing endothermic processes. All right, whenever you're breaking bonds, endothermic. So, all right, we don't break the covalent bonds anyways. Well, it's not being broken. Only two that are being broken are this one and that one. So, all right, so we got 26.5 grams of ammonium chloride dissolved in 200 milliliters of water. The water drops 8.5 degrees. C dissolving reaction letter A. How much energy did the water absorb? Okay, so the way we do this guy is we use this guy Q equals mass times change in temperature times specific heat. So we have this beaker with some water in it, and we now, since this stuff is fully integrated into the solution, we have a new substance here. So there's going to be a little, for this thing, there's going to be a little asterisk that says we don't know our new specific heat, but we're assuming it's very close to 4.18. So they want you to use 4.18 for this guy. They want you to use the temperature change here, which is 8.5. And they want you to use the total mass here because it's a new solution. This is 200 grams. And this is 226.5 grams. And you solve for Q. Alright, so 226.5 times 8.5 is 4.18. 8,047. 8,047. And that's joules. Alright, so next it says the cup. Alright, the cup in the reaction took place has not worded very well, sorry. So the cup in the reaction that took place has a heat capacity of 33 joules per degree Celsius. Well, for the course of the reaction, the cup also reached 8.5 degrees. How much energy did the cup gain? So this is a good example of just a heat capacity. So in specific heat, you have mass, change in temperature, specific heat. Heat capacity is just a energy per gram for a given set of mass. That's not changing ever. So our cup doesn't change in mass ever. So we see capacity a little easier. But we just do this. 8.5 degrees Celsius. Get rid of degrees Celsius and go to joules. 1 degree is 3 joules. All right, so 3 times 8.5, and go ahead and calculate. 25.5. All right, 25.5 joules of energy. What is the enthalpy change for the dissolving reaction? So this is going to be Q per mole. Okay. Well, what's my Q? It's all the energy. That's going to be the 8,047 plus the 25.5 and 8,047 plus 25.5 equals 8,072.5. 8,072.5, and then the moles, we got to get here. Okay, so 26.5, that's the molar mass. That's awfully close to half. Let's calculate. So we got 26.5 grams. Get rid of grams. You go to moles. 1 mole is 53.4. So we're dividing 0.496, probably could be considered 0.5, 0.496. All right, divide them up. We got 8,072 divided by 0.496 equals, here we go, 16,274 joules. So that's 274. So 274 joules per reaction cycle. Now, in this case, this is per 1 mole of ammonium chloride. Since I divided by the ammonium chloride, that's per 1 mole of the ammonium chloride. And in our reaction, that's what we used. So we got to be very careful here that we don't, if we need to double it or triple it based on how much is actually used in the reaction. And first we can just change this to 16.2, kilojoules, and that is my delta H. Perfect. All right, so moving along here. All right, 100 grams of ammonium chloride is dissolved in water. How much energy will the water gain? Use enthalpy from above. So the enthalpy from the last one was, let's grab it here, one quick second. All right, 16.2 kilojoules. All right, so that's what I'll use. All right, so the delta H is 16.2 kilojoules per reaction. All right, so let's do this way. 100 grams, get rid of grams, and go to moles. 1 mole is equal to 53.4. Get rid of moles and go to kilojoules of energy. This right here is delta H. So 1 mole equals 16.2 kilojoules. And there we go. 100 divided by 53.4 times 16.2 equals 30 kilojoules of energy. 30.3, I believe. Holding 3 sake figure, I guess. 30.3 kilojoules of energy. All right, let's go to the next one. So energy by conservation. So this is the general situation here where the multiple ways to calculate delta H. Water evaporates off a sample liquid. The remaining water is warmer, cooler, the same. All right, so we have water, and we are first of all we're only breaking bonds here. We're going to break bonds so these things can. So if you're breaking bonds, that's endothermic and it's cooler. Write the reaction for vaporizing water. H2O liquid goes to H2O gas. Using the enthalpy tables, calculate the enthalpy of vaporization. I'll grab my workbook here. Like I said, I'm not going to be posting this on the screen for you. The liquid is 285. All right. So this guy here is 285. And then this guy here is gaseous, and it's negative, by the way, negative 241. All right, so simple example here. It wants me to calculate the vaporization of water. It wants the delta H on this particular process. We call it vaporization, but really that doesn't do much for us. Just tells us the type of reaction. So it's products minus reactants, so it's 241 negative minus a negative 285. And remember, 2 negatives is just adding, so negative 241 plus 285 is positive 44. All right, so once again, that is endothermic. 44 kilojoules per reaction cycle. Using the enthalpy tables, calculate the enthalpy of vaporization. I guess I just did that right there. How much energy do you need to convert 9 grams of liquid water to a vapor? All right, let's do that right. I'll do that right here. 9 grams. So this is this guy right here. Dot line, get rid of grams. Go to moles. 1 mole is 18 grams for water. That's a whopping 0.5 moles. And then for every 1 mole, 44 kilojoules of energy is required. And then that's half of that, which is just 22. 22 kilojoules of energy. All right. Hydrogen peroxide decomposes in water and gas, and oxygen gas. There we go. Calculate the enthalpy of the reaction using enthalpy tables. All right, so we're doing it again. Get our values down. Let's say this is a gas, this is a gas, so that's going to be negative 241. That's located right there. This guy is 0 because it's based on formation from elements. And let's go ahead and get our hydrogen peroxide. All right, negative 187. We'll assume that this is liquid. So negative 187, only one listed on the table. All right, so products minus sum of all the products is just going to be negative 241 minus 187 minus a negative 187. And this is going to be an exothermic reaction, so negative 241 minus a negative 187 is negative 54. Negative 54 kilojoules per reaction cycle. And there's still only one of these guys going through this thing, so there's this thing does not balance. I'm going to fix that a little bit here. All right, so I put the 2 here, but I think I'm missing a 2 right here. So 2 is 4, 2 and 2 is 4, so I do in fact need a 2 here. Okay, so let's fix this math here, and we'll fix the whole thing. This is luckily why I have this problem here to begin with. So we can see an example like this. All right, so let's just change this. All right. Perfect. All right, so now this one gets multiplied times 2. We're going to get negative 241. All right. Minus, and then we're going to have 2 of these guys. And I got to multiply this one times 2, which I didn't do. All right, minus, and then 2 times 187, and then what we get here. All right, so it's going to be this guy here is 482. All right, so 482, and it's negative, minus 2 times 187. 187 times 2 equals negative 374. Remember, this is negative. So minus a negative, so minus a negative 374. All right. $108. So we got ourselves a negative 108. Now that's kilojoules per reaction cycle. And because we have 2 here, that's for 1 mole to go through. I need 2 moles to go through. So the delta H for this reaction is 2 times that, which is a negative 116 kilojoules per reaction cycle. Write our formation reaction for each substance in its process. Okay, so we have hydrogen plus oxygen yields H2O2. Now we balance this thing. Looks like it's balanced. And of course, the delta H for this reaction is a negative 187. And then for the water, it's H2 plus 1/2 O2 yields H2O. And the delta H of formation of this guy is negative 241. And there is nothing else for oxygen. Oxygen just goes from oxygen to oxygen, and therefore the delta H for this guy is 0. All right. Using Huss's law, calculate it out. Okay, so let's take this guy and let's flip it around. I think this box is supposed to be somewhere else, but let's just solve it out here. So we need to use Huss's law to figure out this thing. I want that reaction to run, so I want flip my reactions around until they equal that process right there. So I want this guy to get flipped because I want this guy to be a reactant. And then their two are good as far as products are concerned. I'm not even going to use the last one. So I'm going to flip this guy to being H2O2 H2 plus O2. And this is going to be a positive 187. And how many? We want to double this thing because I want 2 of them. So times 2, 2, 2, and 2. Multiply this guy times 2. I'm going to get 187 times 2. 187 times 2 is 374. So that should be, yep, 374 positive. All right, and then I'm going to take this guy here and leave it alone. So I have H2 plus 1/2 O2 yields H2O. All right, how many do I need here? I got, well, you can, a couple ways. You can look in the overall reaction, how many waters are going to be there. Or you can look to cancel things out that aren't going to be there anyway. So, for example, the hydrogen has to cancel. So I need 2 here for sure. And so I'm going to multiply the whole thing times 2. 2, when you multiply a fraction times 2, just multiply the top times 2, and then 2. If you take a moment and add everything up, you'll see that we're going to get the same reaction we had up top. So, all right, the hydrogen cancels. This guy, by the way, was a negative 241 times 2, negative 282. All right, I think that's correct. I didn't do it wrong. Yep, and I think that does also match our reaction. All right, there we go. All right, so these guys cancel. We get 2H2O2 goes to and from 2 O2s plus 2 H2Os. And at this point, we should be able to add these up. And I just messed up my doubling there. So I'm going to erase that here for a second. Because 241 times 2 is not what I had there. So let's go ahead and fix that. So that's going to be a negative 482. All right, and add those guys up. So negative 482 plus 374 is negative 108. All right, so delta H equals a negative 108 kilojoules per reaction cycle. And what did we get up top here? 108. Negative. So these two methods are basically the same thing. They are the same thing. One's a shortcut of Hess's law. So either way, they get the same answer. All right, so liquid hydrogen peroxide can decompose into gaseous steam and water. How is the entropy of this changing over the course of the reaction justify? Okay, so we have H2O to liquid going to H2O gas plus O2 gas, and of course there's 2 of these, but It is increasing, positive delta S, and this is due to increased movement. Using standard entropy tables provided, calculate the value of the entropy change for the reaction below. Okay, or actually for the change provided above. All right, so again, I'm going to use our tables here. I'm going to put the values above here now. Let's find our values. So H2O2 is at 109. This guy is 109. The H2O gas is 188. 188. And the oxygen is 205. Notice that this isn't more of an absolute scale. So elements, it's not based on formation from elements. With that being said, oxygen's not zero. So 2 times each of these guys. So this guy goes times 2. This guy goes times 2. Add everything up. And there we go. $581. Okay, and then this guy is just, what, 218. So the delta S for this reaction is equal to 581 minus the 218 equals 363. And this would be in joules, joules per mole Kelvin. And there we go. All right, next, using the standard entropy tables, provide, okay, this is going to be this answer right there. All right, so we got a new reaction. The reaction proceeds at STP. What's the sign of entropy change? Gas to a solid, so I'm losing movement, losing disorder, negative delta S. Is the entropy of the reaction sole reason for spontaneity? No. In fact, this is not a spontaneous situation. So the reaction is proceeding, so delta G equals delta H minus temperature times delta S. And this, of course, is negative. Negative times negative, that was positive. This is negative. So for this to be negative, this also needs to be negative. So for each of the following indicate the change. Okay, so solid to gas is increasing movement, and increasing movement. 1 gas particle to 2. All right, so in this situation, okay, there we go. Hydrogen peroxide spontaneously decomposes into water. What's the sign? Okay, so this is negative. It's exothermic, and it's increasing in movement. All right, using the entropy change in question 10 and the entropy change in 8, determine the value of delta G. All right, so let's just get these values here quickly. So the entropy change up here was, all right here, almost got it, was positive 363. So this guy here is a positive 363 joules per mole Kelvin. The delta H was on the previous page, and that one is getting on here. Negative 116. Okay. So we got, now the one thing I gotta be a little bit careful here is of units. So this guy is a negative 116 kilojoules per mole Kelvin. Alright, so actually, let's take this guy and erase it. So I wrote the wrong spot. So we're looking, alright, negative 116 kilojoules per reaction cycle. So in this case, delta G is equal to delta H minus temperature times delta S. Sometimes I do put a divide by 1,000 here just so that people remember to put this in kilojoules. So negative 116 minus the temperature, which is, this must be STP, I guess, 298, which is standard for thermodynamics, times delta S, which is 300. Now I'm going to go do this on the fly, 0.363. All right, there we go. So 298 times 0.363 is 108. Okay, so I have a negative 116, and then it is negative 108 equals plus 116 is a negative 224. Is negative 224. And this is going to be in kilojoules per reaction cycle. All right, using entropy change. Okay, so I just did that right here. This is all right there. And then 15, it says liquid methanol evaporates at room temperature, but so does water. Does methanol spontaneously evaporate at room temperature at 298? Okay, so this problem here, it wants to know, is delta G positive or is delta G negative at room temperature? Okay, so let's go ahead and do this. So we find methanol, and the reaction here is going to be CH3OH from a liquid to and from gas, CH3OH, and then gas. So what they want you to do, the overall idea of this particular problem is to solve your delta G. So delta G equals delta H minus temperature times delta S. Okay. Now it says liquid methanol evaporates at room temperature, but so does water. Does methanol spontaneously vaporize at room temperature? Okay. Now evaporation is a little bit different phenomenon where we simply have a beaker of water and individual small particles just have enough energy to escape the surface. This is not vaporizing. So the delta G at room temperature for this process for boiling water would still not be negative. It's going to be positive. And it's going to be, delta G is going to be positive at 25 degrees Celsius, but at 100 degrees Celsius, it's going to, delta G just becomes spontaneous. Delta G equals 0. And then over 100 degrees Celsius, increasing over 100, this thing just ends up becoming negative because it runs, it boils it all the time. So we just want to know, is it going to vaporize? Okay, so that means, is it going to boil? So what I'm going to do really here is I'm going to try and find, what's the boiling point? When does this thing become spontaneous? So my reaction here, let's just find our values for this guy. Methanol liquid, methanol solid. Now for this one, I'm going to use at 25 degrees Celsius. That's what we're doing this one. On our chart, you'll find that there's a delta G column and it only runs at 298. So methanol liquid is going to be, this guy is a, now I'm not going to use this guy, I'm going to use this, delta G equals the, let's go with the sum of the delta G of the reaction equals the sum of the delta G. Let's just start that over. All right, so the delta G of the reaction, all right, equals the sum of the delta G of the formations of the products minus the sum of the delta G of formation of the reactants, and away we go. Okay, so the methanol liquid is a negative 166, and the methanol gaseous is not a whole lot different, negative 161, negative 161. All right, nothing to multiply by, so just products minus products, 161 minus a negative 116, and you'll see the difference is not a huge amount. Looks like about positive delta G, was it a positive 16? Well, it's a 161, so I should read that correctly. So it's going to be 161, and that would be a negative here. So we're going to end up with a negative value. Negative 45. All right, so in this case, the delta G equals a negative 45 kilojoules. All right, and let's make sure we got this right. Double check my numbers. Typically, evaporation would be endothermic. All right, so methanol as a gas is 161. Here we go. Ash with the numbers down wrong. 161, and liquid is 166. All right, so there's a bit of a transferring issue here. 166 and 161. So let's redo this. Getting a little bit worn down here. So 161 minus the 166, and we want to have a positive because evaporation typically would be positive. All right, so here we go. 166. Knew they were really close. All right, so, and this is just adding here, so we're going to get a positive value, and it looks like 5. Okay, 5 kilojoules per reaction cycle. Perfect. Biggest issue is, I find with this formula is just bookkeeping. All right, and all right, what happens to the magnitude of delta G as the temperature goes down? Okay, so we have delta G equals delta H minus the temperature times delta S. So in this case, I have delta G is negative, all right? I have delta H, which is a positive reaction, okay? And the last one here, one thing that we would do on this guy here is let's just make sure we got this guy here, is this only runs at 25 degrees Celsius, okay? So the answer is that, all right, that at 25 degrees Celsius, this thing is not going to run on its own, okay? It might evaporate, but it's not going to boil. So it's not running spontaneously. So we want to know what happens when I raise my temperature. So this is a pretty common phenomenon where we want to know how delta G is affected by changing temperature. Okay. So in this case, for this process, we know delta H is positive. Okay. And I want to know how this thing is being affected by the changing temperature. I'm going from a liquid to a gas, so this is a positive. Positive times negative is negative. So as I raise this number, that means my delta G, well, it approaches 0. It's positive then, so it's becoming more and more negative. So the answer is what happens when the delta G, the temperature goes down? Okay, so that goes up. So as it goes down, delta G becomes more positive. Okay. What happens as the temperature at which the reaction becomes spontaneous? All right, so we would need to do this way. Delta G equals delta H minus temperature times delta S. All right, so this is going to take a little more work because we need to solve out this guy here, and then put 0 in for this guy, and then we could solve it out with that. So let's do this here quickly. It's not a huge amount of work here. Methanol, although methanol liquid going to methanol gas. And I'm just going to jot down these values here quickly. So for methanol liquid, I got the delta H is located here. The delta S is located here. So the methanol liquid is negative 238. And then we have this guy is negative 200. And then delta S is 126. Hold on a second. Yep. 100 and all right. Take a moment, calculate the delta H for this reaction using that information, and the delta S for this reaction using this information. All right, so this is positive, and it is 38. This is minus, okay, looking for T, and this is positive 0.113. And I must subtract this guy over, solving for T, so it's going to be a negative 38 divided by a negative 0.113, and we get our temperature, which it becomes spontaneous. All right, so they're going to get a positive value, so 38 divided by 0.113, and 336 Kelvin. 336 Kelvin. Now this is when delta G equals 0. Alright, so that is the answer to this question right here. Okay. Calculate the entropy in joules mole per Kelvin for the reaction provided here. So we have a reaction, delta H equals this, delta G equals that. So this is another way of solving for delta S. So delta G equals delta H minus temperature times delta S. Okay, so the delta H is positive 20, it looks like. So this is just 20. Delta G looks like a negative 24, minus my temperature. Don't see, well, I'm assuming we'll go with standard temperature then, 298. And then my delta S is what I want to solve for. This is one of two ways of solving for delta S. The other one is right here. Okay, so we take negative 24 minus 20 is negative 44, divided by a negative 298 is 0.147. So it is delta S equals 0.147. Now this would be in kilojoules per mole Kelvin. So if you want to make it in joules, it'd be 147 joules per mole Kelvin. All right. Hydrogen peroxide decomposes spontaneously at what is delta G at equilibrium. Okay, so in this case, we must have all the information for this guy already. I think we solve it out here. I'm going to do it again here quickly just because I can. All right, so I'm going to use the delta G values for this guy. So we're going to just running some equilibrium stuff through here. So the equation is H2O2, two of them, goes to and comes from H2O, two of them, plus O2. Okay, I'm going to use my delta G values to met that temperature. So for H2O2 on this guy, negative 120 is for this guy. All right, negative 120. And then the water gaseous is right above it, and negative 228. All right, so negative 228. All right, so let's figure this here quickly. So this is going to be times 2 is all right, so we have all right, what's the equilibrium constant? Okay, so in this case, we have a formula which is delta G prime, which is what I just calculated, equals negative RT natural log of K. All right. So in this situation, you want to make sure that you have your table with you, your equation, so you know that equation, and you'll find it under the thermodynamics, electrochemistry section, and then you want to make sure you have your units correct, your R correct. So this is in kilojoules currently, okay? So my R is given in joules. So I'm going to just keep this in kilojoules. So it's going to be negative 216. Now that's a really big delta G, by the way. So for this equation, it's likely going to get aired out. But this is going to be a negative. It's 8.31. You'll find on your laminated sheet, it is 8.314. You notice it says joules. So this is going to be 0.00831 times 298. We never change that temperature ever. And then the natural log of K. Alright, so it's a long video, sorry about this. So negative 216 divided by 0.00831 divided by 298 is going to be negative 87. So negative 87 equals the natural log of K. So raising this thing inverse powers e to the negative 87th equals e to the natural log of K just equals e to the 87th, negative 87th, equals my K value. And so I'll second log that function, second natural log the previous answer, and I get 1.31 e to the 38th, 1.31 e to the negative 38th, negative 38th. Alright, so that's my K value. Now, in this situation, we want to make sure we didn't make a mistake. We're looking for a delta G, looking for a K value that would be bigger than 1. Now, this guy is not bigger than 1. So, is there a mistake here? Alright, so I had a negative here, and this is my direction. I have a negative right here, and I think I forgot that guy. Okay, so in this situation, I have a negative, and when I divide that, it becomes positive, so this is actually a positive A7. Okay, and all it does is change that number there a little bit, and becomes much larger. We would like always important to look at your number and say, does the number make sense? I have a negative delta G, means that I am pushing quite well in the direction of products. This thing is pushing this way. So if you get a really small like that, that's not making sense. So that negative came off of there, positive, and so it's going to be the second log, natural log of 87. And now we're getting a much larger number, 6e to the 37th. Alright, so 6.0 e to the 37th. And that is my K value. Alright. Anytime delta G is negative, the reaction is not the reaction of equilibrium, it will move towards the products. Anytime we're negative, we're moving this way. What's the difference between delta G and delta G prime? This one is at STP. Right. Student hypothesis is not possible to have a positive delta G if the delta G prime is negative. Well, it depends on, the reaction. If your delta G is prime's negative, the prime doesn't mean anything. If it's for the same reaction, obviously, then if we have this guy, reactants, products, okay, and we're right here, and if your delta G prime is located here, if you have a delta G prime, okay, that's negative, that means to get to the end, you're going to have to end up over here, all right? So you're moving this way to get to here. Delta G at that point equals 0. Is it possible you have a positive delta G? Well, you would need to alter your concentrations, and you could just be over here. You need to ramp up your reactants and drop your products, and you'd have over here, delta G would be positive. And of course, it would eventually move to the same location. So, is it possible? Yes. You would just need to, all right, change reactant concentrations, change concentrations. Okay. And that ends our thermodynamics.